Okay, good afternoon. Let's see, administrative things. We're having an exam next week. Yay. It has a group part, so you need to have groups. I'm hoping that for the most part they'll be the same group that you had in midterm one, although I understand that some people have dropped the class and so on since then. But you should make sure your TA has you organized in groups. It's not the same kind of group thing as in midterm one. The way it will work is there will be one problem that you do as a group first, and then we'll collect those, and then you'll do the individual part, which will be different from that. So it's not like redoing the same problem. Generally speaking, we've had the group problem be the drawn environment diagram one, and I'm not promising that'll be true this time, but it's sort of looking probably that way as of this moment. Is there anything else I have to say about the exam? Yeah. The usual things, question 0, your name, ... What? Yeah, it's here at 7 o'clock Wednesday. Same as midterm 2, basically. Okay, that's it for administrative things. We left off last time talking about streams with this really beautiful example that's up on the screen about generating the infinite stream of all the prime numbers. So the thing that's magic about this is that it lets us write programs as if we had already computed all of them, which makes things simpler. Of course, it's not so magic that you don't still have to do the work of computing them. As you ask for the stream coder of this, the stream coder of the stream coder of this stream, each of those takes longer and longer to compute because you're trying more factors. Basically, it finds the next prime by the same sort of looping flow of events as in the prime question mark example, where what really happens looks like that iterative thing. Same thing is true here. Basically, what we've constructed is an iterative process called find the next prime. But we didn't write it that way. We wrote it as find all the primes at once. So it's really a thing of beauty. And underlying it is the other thing of beauty, that we can separate out the sequence of events in the running of a program from the organization and shape of the program. And that's really nice. What computer science is all about, really, is trying to hide from computer users how computers work. Because, computers are ugly and messy, and we don't want people to have to think in ugly, messy terms to use them. And so our job as computer scientists is to take all that ugly mess and sweep it under the rug. And the rug in question is abstraction. And so this is an abstraction that lets us sweep under the rug exactly what happens when in a computer program. And I put back this sort of iconic picture showing us how we started with a plain old list program to compute a range of numbers. We made this tiny little looking change that looks as if it shouldn't do anything at all, but it had this profound effect on how the program actually runs. And then we did this thing that looks like an enormous change, so much so that it should break the program, and it turned out not to break the program, and that was how we got into the notion of infinite streams. So that's all just review of last time. So the next thing I want to talk about is something that I think in the book they do called implicit stream definition. So the way I made the integers let me back this up a bit, is I wrote this ints from procedure, which is basically the range procedure without the base case. And then I invoked the procedure to generate the stream integers. But we don't have to do it that way. We can also do something else like this. So I just said define ones, constream one, ones. And again, this looks like it can't possibly work because I'm trying to use this variable ones that I haven't even defined yet. So how can that make sense? And indeed, if I had done it with cons instead of constream, it wouldn't work. But what happens here is that we say, okay, ones is a pair whose car is 1 and whose cdr is a promise, but in this case the promise is very simple. It's ones. That's the entire promise. Now at the time I make that promise, there is no ones. But having constructed this pair using constream, now we do the define, and so in the global environment, so this is the global environment, there's a binding from the symbol ones to this pair, and now that I've done that, I can cache in this promise. Okay, so ones is just a stream of infinitely many ones, because when I cache in this promise, I get this pair again. And if I take stream cdr of that, that's the same pair again, and so on. Okay? So the first thing to note about this is that it's sort of similar to this structure. Right? We could use setcdr, bang, to construct a pair that really was a circular list in which every element was 1. The difference is the stream way is functional, this way is not functional. In order to make this, I can't just say cons and get a structure that looks like this. I would have to say define ones like this. Define ones to be, let's say, cons 1, 2, and then say setcdr bang ones, ones. So that's how I could do something equivalent to what I did for streams using mutation. But the stream version, there is no mutation. The thing I set up in the first place is the thing. So this is an example of a way of doing functionally something that we had previously learned how to do non-functionally, and it looked at this point as if we had to abandon functional programming in order to get a circular structure like this, but now we see that that's not so. We can make circular structures functionally using streams. So once I have ones, I can use ones to make integers. I can say define ints constream 1 nat plus ints ones. Oops. Uh-oh. What happened? Stream map, thank you. Do that again. Define ints constream 1 stream map plus ints ones. And there they are. Okay. So how does this work? Here's the stream ones. And now what about the stream ints? Well, its first element is 1, because it says constream 1 something. So we explicitly gave that first value of 1 here. And now what we're going to do is the remaining element of ints, this part, is what we get by adding up the stream ints and the stream ones. So what's 1 plus 1? It's 2. Well, until now I didn't know the second element of ints, but now I do, so I can say 2 plus 1 and get 3. 3 plus 1 is 4, and so on. So we're generating each element of ints just in time to add 1 to it to get the next element of ints. This is called implicit definition because I didn't define any procedures. I didn't say, here's the process by which you generate elements. I just used the delaying effect of constream to be able to construct ints, quote, all at once, unquote, without procedure calls. Well, without calls to procedures that I have to write. I just use stream map to do this. Notice, by the way, it's really, really important that constream 1. You couldn't just say define ints, stream map plus 1's ints or something. That wouldn't work because it's important to have the delaying effect of constream. Right? It's not only that we need that first 1 in the first position in order to do the first adding, it's also that we have to make sure that the stuff in the box here gets delayed by constream until we have a chance to set up a value for ints. Okay? Any questions about that? This is a good skill to have. If you look at some of the old midterm questions on streams, there are things like, define mystery, constream A, constream B, stream map, blah, 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 and says, what are the first 10 elements? So that's something you ought to be able to do. And there are homework exercises about it. Okay. I already said last time, but let me repeat it, that this reordering that we're doing, we only get to do that because we're doing functional programming. So it's not a good idea to mix streams with mutation. If you try to do both of those together, you're likely to confuse yourself. Because remember, the sequence of events in your program is not the sequence of events that it looks like. And so if you have blah, 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 and then set bang something, and then blah, 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 it's very possible that something that's before the set bang in your program might not actually be computed until after the set bang. So this is one more example of the virtue of functional programming in allowing reordering. And it's related to the way in which functional programming helps us with parallelization, because that's kind of like reordering, where we don't know exactly what happens first. Okay. There's a lot of little subtopics here, so this is choppier than the usual flowing lecture. I'd like to call your attention to the similarity between what we're doing with streams and normal order evaluation, which you learned about back in week 1 and we haven't looked at since. So remember, Scheme uses applicative order evaluation, which means when you do a procedure call, first we compute all the argument values, and then we call the procedure, and we give the procedure the values, the actual values themselves. Normal order says, We call the procedure, and it gets the argument expressions, and it can decide whether it actually needs to evaluate them or not. So imagine if Scheme used normal order evaluation. Then we could just do plain old cons, and that would have the delaying effect that constream has. Basically, normal order means everything's a special form, right? So we wouldn't have to make a special case of constream. Now, that's not quite true what I just said, because in normal order, the way we looked at it in week 1, when you call a primitive, the argument expressions are evaluated. And cons is a primitive in Scheme. So normal order evaluation wouldn't quite do the trick. We would have to make an additional rule that cons, that not all primitives force argument evaluation. Only some of them do. Okay? We're going to be revisiting this idea later on when we actually build a normal order Scheme interpreter. So we'll see how that plays out. But the reason I'm bringing it up right now is, back in week 1, why didn't we use normal order evaluation? Well, because of examples like, if I say define square of x times xx, and now I ask to compute square of some long computation. Let's say this takes an hour. In applicative order, we spend the hour to compute this, and then we get the answer 3 after an hour of chunking away, and then we go times 3, 3. That's what applicative order does. What normal order does is it says times some long computation, some long computation. So we're going to end up taking 2 hours, once for this one and once for that one. And that's not very good. And streams have a similar possibility for inefficiency. Namely, every time I say stream coder of some stream, I'm not just asking, what does the coder of this pair point to? I'm asking to cache in a promise. And all the examples we've looked at this week, the promises have been pretty simple. Well, except for the prime number one, where as you get further and further down the set of primes, they get slower and slower. So let's take that one. Suppose I ask for the 3,000th prime number. Okay, and let's say it takes some amount of time to figure that out, non-trivial, I don't know what it would be. And then let's say I ask for the 3,000th prime number again. If I had a list of 3,000 primes, it would be quick to find the 3,000th prime. I'd have to still coder down to that far in the list, but I wouldn't have to actually do all the is this divisible by that computations over again. So that's a potential for inefficiency in the use of streams. And the way we get around that is I actually lied about the implementation. I told you I was lying, and I said I'd come back and explain it. And if you look in the book, what they do for delay is they go ahead and make the thunk that computes the expression when invoked, and then they call a thing called memoize, which the code is in the book. I won't bother showing it to you, but you should remember what memoization is about. Memoization means whenever you compute some value, you remember what the value is. We did this for Pascal's triangle or something. Right? And if you remember the value, and then when you ask for the same value again, first thing you do is look to see, do I already know the value? If I do already know the value, then I don't have to compute it again. I can just return the value that I remember. And that's how streams work. So every promise isn't just the procedure that has the expression as its body. It's actually a more complicated structure, which it's a procedure of no arguments. When you invoke it, it has a local state variable that's true or false, saying, have I been invoked before? If the answer is yes, it has another local state variable, which is the value that I got the first time. And if have I been invoked before is true, then we just return the value of that local state variable, which never changes. Yeah?
Is there a way to make it not memorize the promises? Because this kind of thing would invalidate something like random.
Okay. Good question, but you're wrong. He wants to know, is there a way to make it not memorize the promise? Because, he says, if we memorize things, then we can't make a stream of random numbers, because each random number you want to be different. So first let me answer the question you asked. If you use Scheme's built-in delay, it memoizes, and you're stuck with that. But of course, it's very easy to make a non-memoizing one of your own, if that's what you want to do. But the one in Scheme does memoize, and that's how it is. Now, about random numbers, I'm glad you asked. It's true that you can't do the following thing. Let's say I want a stream of random digits, so I'll call random 10, which gives me a random number between 0 and 9. I can't say define rands constream random 10 rands. Because if I do that, I indeed get the same random number every time. But I can do this. Define a procedure randstream, which when invoked says constream random 10, and then call randstream again. And now I'll define rands to be an invocation of randstream. And now I get random digits. Okay? The thing is that when I defined the procedure up here, I call random 10 anew each time. Now what is true, oops, that's not what I meant, is that if I look at rands again, the first 10 elements of rands again, I get the very same first 10 elements. Okay? So if I try to start over again in the stream generating random numbers, I do get the same random numbers repeatedly because of memoization. But you just refrain from doing that. You don't start over again. You just keep going down the stream. Okay? Right. Okay. There are actually three sort of big ideas about why you might want to have streams. The first one, the thing we started with Monday, was making more efficient a finite computation. So this was the thing, I want to know whether a million is prime or not, right? And we were able to do that quickly instead of slowly by using the stream of all the factors of a million. And then the second thing was we can use streams to represent infinite data streams. So not just the first 1,000 prime numbers, but all the prime numbers. Okay? And the third point about what streams are good for is the representation of time-varying information. And the thing about the stream of random numbers is a good way into that. Because the random numbers are basically time-varying. You know, each time you ask for stream coder of that random number stream, you're getting a new random number. In the world outside of CS61A, the word streaming is often used for, you know, stuff that varies over time, the kind of data that varies over time. Like, for instance, you've heard the phrase streaming audio and streaming video, right? Which means that instead of just plopping down a whole song or a whole movie or whatever in your computer, some server is sending you the next little bit of music or the next little bit of picture over and over again continuously. Okay, so it's a stream of data. And it's not probably implemented in exactly the way that we're talking about here, but it really is the same idea, which is we want to find a way to represent information that's sort of coming in over time. And we want to do it so that we can write the program as if we have the whole song or the whole movie, when really we get each little bit as we need it. Okay? And why would we want to do that? Because we'd like a functional alternative to object-oriented programming. And what I'm really answering now is the question, why is this stuff in Chapter 3 anyway? Since I've been telling you all week that streams only work if you're doing functional programming, why isn't this back in Chapter 1? And there are two answers to that. There's sort of the trivial answer and the profound answer. The trivial answer is that we needed some of the mechanisms of mutation to build streams. So we need, in particular, a way to talk about the environment that has that stream ones in it. Okay, we needed to know, we needed the environment model evaluation. We can't use substitution to talk about streams. So we needed some intellectual scaffolding to allow us to talk about streams. That's one answer. But a deeper answer is, Chapter 3 is about computing stuff that changes over time. Chapter 1 is about asking timeless questions, right? The typical mathematics question, like, you know, what's the 43rd Fibonacci number or something? Well, it's the same answer now as it was back when Fibonacci lived in 13, whatever it was. Is that right? I have no idea what century, but later than Euclid, earlier than us. Anyway, it doesn't change. That's very different from stuff like, I have a bank account and I'm making a series of deposits and withdrawals, and how much do I have in the bank right now? And all through Chapter 3, we've been saying, when you're writing a program that's trying to model a sequence of events in time, the natural way to do that is for there to be a sequence of events in the time in which your program is running. So at some point you'll say, you know, set bang balance plus balance amount, right, in your deposit procedure. And all the stuff we did with object-oriented programming has that nature. But we saw just last week that stuff that works with mutation is problematic when there's a lot of parallelism going on because of the possibility of concurrency bugs. And gee, it would be really nice if we could have a functional way of doing that. So can we do that? And the answer is going to be yes. And let me start by showing you this. Okay. So this is like that random stream procedure I wrote just a moment ago, except the thing that I'm doing over and over again is calling Scheme's read procedure, which reads an expression, right? Like a number or whatever. So now suppose I say, show stream the result of calling user stream 5. Well, nothing happens. Why? It's waiting for me to type something in. The read procedure is waiting for me to type something. So I'll say, let me start with an initial balance of $1,000, and then I'm going to deposit $100, and then I'm going to take out $300, and then I'll deposit $50, why not? And then I'll deposit $500, and then I'll take out $100. Oh, look at that. So the behavior of the program is it's interacting with me. But I can write programs that call user stream as if I had the entire future history of my interaction available right now. Okay, so this is a way of seeing into the future. So let me just do a very, very simple version of this. Let's okay, so here's my account. And let me go ahead and say, show stream my account 5. So my account starts with $1,000 in it. And now what I'm going to do is add to the stream my account, which is the stream of all the balances that my account is ever going to have into the future. So I'm going to add to that stream the stream of all the deposits and withdrawals I make in the future. So I have $1,000 to start with. So I'm going to deposit $100. I'm going to withdraw $300. I'm going to deposit $400. I'm going to take out $60. Oops, take out $60. And then I'm going to deposit $1,000. Okay, and now the stream my account is not the numbers that I typed in. It's the running sum of the numbers that I typed in. So I started with $1,000 initially. I added 100. I subtracted 300. I added 400. I subtracted 60. And notice that it didn't show me the last thing because of the delay, the way the delays and forces work out. What is available for me to see is always one step behind the last number that I typed in. But that doesn't matter because this stream really goes on infinitely. It's only because I called show stream that we have the artifact of seeing 5 numbers rather than 6 numbers. But that's an implementation of a bank account, which is the sort of paradigm of modeling time-varying local state without any mutation at all, entirely functionally. And so that's why this is in chapter 3, because we can use streams to write a program dealing with the whole future history of a sequence of events in time. And so things that use randomness, we have the stream of random numbers, and we can just pull values out of that stream as we need them. Okay? So isn't that kind of nice that you can do that? People only really do this in the real world in special cases, like streaming video, let's say, where you really do want to think of, I have this movie. So you actually download something, you click on a link in the web page at wherever you buy your music from, and something pops up in your computer, and that something is a song that hasn't been played yet, right? And when you try to play it, it opens Real Player or QuickTime or whatever you use, and then it starts pulling stuff off the net, right? So, boy, I tried to get this whole long opera and it all downloaded to my computer in the blink of an eye. Well, no, it didn't. What you got was a little token, which when you click on it, it starts really giving you the data. And that really is the model that we're using here, although, they're not writing it in Scheme or any of that. It's the same idea. But if it's bank accounts, they mostly don't use streams as the way to do it. Although they could in principle, they mostly don't. Why? Well, it's a little counterintuitive, for one. But also there is a problem, and I'm only going to kind of give you a rough glance at this. The book goes into more detail about it. The thing I just showed you for the bank account, it's pretty magic and you should be impressed by it. But it only works this nicely when I only have one bank account. Okay. If we go to the ATM and lots of people have accounts using the same ATM, and more importantly, the same thing that was problematic the other way of doing parallelism, which is what happens if two people go to two different ATMs using the same account at the same time. Well, we're not going to have concurrency bugs. The fact that we're doing functional programming really does mean that we can't get wrong answers the way you can using mutation. The problem that we have is different. It's how do we sort of merge the data stream coming from this ATM with the data stream coming from that ATM. And it's in the course of doing that that you get the complexity back in that we gained by not using mutation. And the issues have to do with sort of timestamping of events, right? So, well, think about it. Let's say there are only two ATMs in the world, just to simplify things. And now I want the stream of all possible events. Well, so you can imagine that each ATM has a clock. And so what we get from the ATM is not just the amount that you deposited or withdrew, but also when you did it. And then we could write a little merge procedure that says, okay, look at the next value from this ATM and the next value from that ATM. See which one came first, and that's the one that goes next in the combined results. And then we take the one that we didn't use and the next value from this other ATM and see which one came first, and so on. Okay, so that's still straightforward. Writing that merge procedure is very easy and it works with no problem. But here's where the problem comes in. We've solved the problem of two people coming to two ATMs at once. But the way we solved it left us with the following dilemma. Let's say there's ATM number 1 and ATM number 2. I come up to ATM number 1 and do a transaction. Then you come up to ATM number 1 and do a transaction. Meanwhile, nobody's done anything on ATM 2. Well, we cleverly wrote a procedure that merges the results of these two ATMs by looking at the timestamps on the first event here and the first event there. Well, guess what? That program is waiting for the first event on number 2, which hasn't happened yet. Okay? So, meanwhile, my transaction and your transaction can't really be processed until that one happens. You know, it's like when you pull up at a stop sign at a 4-way stop and you're behind some timid old driver who thinks that what the stop sign means is you're not allowed to go again until another car comes along in the other direction. It's that kind of problem that we have, right? We can't decide that this one comes before that one until there's a that one to compare it to. Well, is this problem solvable? Sure. Right off the top of my head, here's a kludgy solution. We program our ATMs so that once a second or so, they generate an event even if nobody's using them. Sort of the zero event. We deposit 0 into somebody's account. Okay, that'll fix it. But now we have things happening at all the ATMs all the time, and we're back to worrying about. Anyway, so it's not totally without complication. Trying to use streams as a way to model time-varying local state is theoretically doable, and it avoids concurrency bugs, but it's not totally smooth sailing. There are some things you have to worry about to make it happen. And the book only goes a little bit further down that road than I've gone, but like everything else, it has footnotes. The thing about Abelson and Sussman is if you actually read all the footnotes, and that is read the papers that the footnotes point to, you know all of computer science, right? So in a certain sense, this book has all of computer science in it, in kind of the same way that that stream has all the prime numbers. Okay, let me stop for questions. Yeah.
For that kind of concurrency issue, couldn't you use a stream to sequence the events arbitrarily, and then have them processed centrally somewhere in still in a stream way? Like have a stream of all of the requests received to the central server from the ATM.
So have a stream of streams, you're saying, basically. That.
No, have a stream of requests that basically it's a const stream of the first request you receive at the central server from ATMs.
Oh, from any ATM.
Yeah.
Yeah, so what he's saying is instead of trying to make a combined stream in which we merge all the ATMs into one big stream in the right time order, let's just let them throw events at a central server and let it generate the stream of requests that it's gotten. Yes, you can do that. What you've done is you've buried a concurrency problem under a rug, and the concurrency problem there is the receipt of connections over the internet. Okay? So what if 2 packets come into your computer at just the same time? What happens? And that actually is a problem, and it does come up, and how it's resolved depends on exactly what kind of network you're on. But for instance, the Ethernet answer, if you have sort of hardwired net connection, and 2 different processors try to throw packets on your local net at the same time is they both fail, and the hardware is built in such a way that the senders of those packets can tell that they failed. And then the software specifies that each of those senders waits a random amount of time and tries again. And the reason for waiting a random amount of time is so that they don't just keep colliding, right? So that's a way of solving the problem. But you do have to solve it. So, one way or another, you're going to end up with concurrency problems to deal with. The concurrency stuff that we did last week was using the model of two processors in the same box sharing the same memory. And those are messier than the kind you're talking about where you have client-server concurrency issues. Those ones are easier to fix. But easier doesn't really quite mean easy. Mostly we think they're easy because somebody over in the EE side has done all the work for us. But yeah. Okay, other questions?